So to quote an old song, this is going to be something like Ed's 19th nervous breakdown. You've gone like 75 million of these seminars or something like that?
Yeah,
The last one was on Fabulous. It was on dimensional analysis, which actually had 2 DVDs made extra and sent to my kids. It was so good.
Oh, great.
Yeah, that was good. Travels to CERN, it just reminds me one doesn't simply walk into Mordor, right? So
No.
I presume you don't just simply walk into CERN, so I'll be curious to see how you did that. And he forewarns me we're going to get a lesson from Mr. Grammar over here about the definitive article in English, and it goes like,
Earth, not the Earth.
see?
That's the planet we live on. So, but anyway,
You're on.
Oh, okay. So thanks for coming. I know there was confusion about the lecture because the servers were going crazy, but I appreciate you being here. So what Bob was referring to is I get crazy when I hear scientists and broadcasters say the satellite is orbiting the Earth. That's not right. Satellites don't orbit the Saturn or the Mars. They orbit the name of the planet. Fill in here, and the name of this planet is Earth. So enough of that. We had the good fortune, my wife who's here today, and I had the good fortune to go to CERN in Switzerland and France just a few weeks ago, and I thought I'd give a lecture on what we learned about the machines they have there for doing subatomic physics, the standard model of subatomic physics and how these kinds of machines are potentially going to change it, search for the Higgs boson, that sort of stuff, and that's what I'll be talking to you about. So this Paul Gauguin painting, which we've all seen, seems to have the right kind of...
Pearl, is the little green light work?
Oh.
Yeah, I agree that it should. The question is, does it?
Little
The
green,
conditional English, you know?
yeah, so just give me a... it's that guy. Okay. So Gauguin...
Yeah, one light lights the other one blows up the universe.
well, that was a concern at CERN when they turned on the Large Hadron Collider back in '07. There was anguish amongst the neighbors. They're worried about black holes. But we'll talk about that. So Gauguin has this painting much more elegantly put in French than here. But basically it says, where do we come from? That's this part. What are we and where are we going? And that's kind of the thematic structure behind the European investment in CERN. So I want to tell you a little bit about how it is that we got there and got a very special background view of what goes on. We have, in the past, 2 years ago, traveled with Scientific American on a cruise where you have lectures. Whenever the boat's moving, they give lectures, and we had such fun on that, we decided to do that again this year. So back in April, we were with Scientific American again, and they have an organization that they collaborate with to organize cruises. And we had 4 lecturers on the boat. Pal Brecky, who knows ball, he was at NASA Goddard for a long time. He's a solar scientist, and so he gave lectures on the sun and its interaction with Earth, and then archaeology. Frank Lindy kind of prepared us for our visit to CERN because he's a scientist there with a special focus, which I'll describe. But anyway, he had lots to say about particle physics and the search for the Higgs boson.
Well, I think the day that the boat was moving and I had the choice of drinking beer or wine or whatever on the deck and going to hear about famine, disease, war, and mass death in history, that would have been a choice. That's a pretty binary discriminator in my opinion.
Well, we had fun with all these people, and then we had this guy from Israel who gave extremely technical lectures on biochemistry. So, real quick, we launched from Amsterdam. We cruised to Basel, Switzerland, and we decided to pay a little extra for a 3-day extension to the cruise to go to Geneva, and that allowed us to go to CERN. And along the way, we saw castles and went to Einstein's house and vineyards, and that's the Max Planck Institute for Astronomy, which was part of that is somebody you all know of. I'll come back and see if you can figure out who that is. A celebrity was in our cruise group. That's me with a world-famous photography educator, and I got a chance to play a little bit with the band on the boat, which was one guy. This is Peter Norton. You know him because of Norton antivirus.
Ah.
I mean, when you He's a very relaxed kind of guy. I met him. He said, "My name's Peter Norton." It didn't ring a bell with me until he started talking about all the boards he's on. He's a very...
Why is he wearing blue cryo gloves?
Because we went to the Institute for Astronomy, and they had him do a little experiment with liquid nitrogen.
Oh. No, real men don't use blue.
No, they just stick their hand right in.
I just stick my hands in and...
So you can see we had stops along the way, and we cruised like everybody else cruises on the Rhine River.
Inebriated.
Inebriated, yes. Wine was provided with lunch and dinner. So the reason we extended our trip to Geneva is we wanted to go to the CERN Large Hadron Collider, and it's a day trip from Geneva. That's what I'll focus on the rest of this lecture. It's and we were surprised to discover that they gave us access, as much as you can have when the beam is running underground, to the compact muon solenoid. And I'll talk about which is a general purpose detector for extending and refining the standard model of subatomic physics, and I'll explain what it is they do there. Incidentally, hadron, the H in LHC, hadrons, any class of particles that experience the nuclear force. So this is in the experiment. They call this the detector. We would call this a giant 12,000-ton construction. There's a human, give you some sense of scale. The beam goes through the center, and then they have these spectacular magnets, which I'll describe in a few minutes.
And they call this compact.
This is the compact muon solenoid. You'll see in a minute also the layout of the experiments. Just like Fermilab in Illinois, they have two experiments using different technologies to do the same physics so they can corroborate each other's results. So here they have CMS. On the other side of the ring, they have something called Atlas, and they collaborate, but they compete as well. Now, if you're just a regular citizen and you go to CERN, which you can do, you can go into this reception dome, which has these very interesting lighting and movies, little pods you can sit in and listen to lectures, 2 or 3 minute lectures on different topics related to what CERN does. And I thought it'd be interesting to show you. There were groups of school kids, and you can see it's like an education center. And they have a reception area across the street, which is very tiny, and that's what the public sees. We were with this group that arranged ahead of time, and so we got a chance to sit in this lecture hall with Frank somebody. He is the public outreach guy for CERN, and he gave us a 40-minute lecture on what they're doing, the search for the Higgs boson and so forth. And that was really set the stage for visiting CMS. We had no idea when we went there that we were going to get access to one of the experiments. So here's how things lay out. There's the city of Geneva, at the end of Lake Geneva, and CERN is centered over here, not far away. The ring, the Large Hadron Collider ring, is a 27-kilometer circumference. It's in a tunnel that was dug 20 years ago or so for something called LEP, the lepton electron something. Now that experiment did a bunch of things. It was at relatively low power compared to LHC, and it was colliding electrons. And so it's been retired, but they used the tunnel for the Large Hadron Collider. Here's the collider ring. And it doesn't exist all by itself. It has some pre-accelerators. There's a couple of synchrotrons, linear accelerators, and so forth that provide proton beams that get injected into this big ring. And I mentioned Atlas. Here's the Atlas experiment is there. And then over here, the CMS. And then there's Alice, and I'll talk to you about what these things are.
Why did they pick Geneva?
Well, there was this, it's a European collaboration. The E in CERN refers to Europe. And they put it here for two reasons. One, political. It's actually split on the French-Swiss border. The other is geologic. This area is seismically stable, and there's a stratigraphy here that allowed them to dig without using complex machines designed to dig through soft soils. They were able to use rock boring technology, which is relatively easy to do compared to digging through mud. Anybody who's lived in Washington, D.C. back when they were building the subway knows that the whole subway construction bogged down when they had to go through clay-type soils. It gums up the works. So, and in fact, the ring is not level. It appears level in this drawing, but actually it's tilted to match the local stratigraphy and keep the cost down of boring the tunnel for LEP. Remember, this tunnel was built for LEP.
How deep is it?
It's 300 meters under, 100 meters underground, 300 feet underground. And also, the ring and the experiments are underground to isolate it, all of them, from cosmic ray background that would otherwise cause a adverse impact on the quality of the science they're able to do. So CERN's been around since the early 50s. It's about the size of ball. They have about €1 billion a year in funding from around the world, actually. The full-time employees, incidentally, only include about 70 particle physicists. The rest are engineers, technicians, construction managers. It's a big, complex machine, and they've done some amazing things. I mean, they've invented these things. The key thing I'll be talking about is the discovery in the early 80s of the W and Z bosons, which were predicted by the standard model of subatomic physics, but were not seen until the early 80s. And finding these bosons and being able to characterize their properties gave the physics community confidence that the standard model actually works, and there's even more evidence has come forth since the early 80s. This is what started the search for the Higgs boson. So LEP is actually the Large Electron-Positron Collider. So they made electrons and positrons back in the 20 years ago, collided the electrons and positrons, they neutralize each other and produce high energy photons. So you see a bunch of really interesting physics they've done, and if anybody wants these charts, I'm happy to share them with you. They've made atoms, they do some side experiments, atoms of antihydrogen, and keep them going for long periods of time, really exotic kinds of matter. 2 Nobel Prizes awarded to CERN physics people, and it's the home of the World Wide Web. Many of you know this, but managing the volume of data they produce became such an issue that Tim Berners-Lee and his colleague Kallio had to figure out a way to manage the volume of data and be able to share it with the huge international community that beyond these 2,400. There's probably 10,000 people around the world who use results from CERN, and getting data out of CERN, processing it, making it visual, and sharing it with the science community was becoming a big problem. So they invented techniques for sharing large volumes of data, going beyond the old FTP, Gopher, Telnet kind of technologies that were born in the early days of internet. And so they take credit for being the first to use the World Wide Web and inventing Mosaic, which was the first web browser. And as they say here, you can still log on to the original website. Dates back 20 years.
What's a CP violation?
That's, yeah, it has to do with parity in subatomic particles. That is, if you imagine these particles that make up protons and neutrons to have a spherical property, that would mean they were uniform in all directions, and no matter how you look at these little particles like quarks, and I'll be talking about quarks here in a minute. But it turns out that there's a left-handedness and a right-handedness to these particles, completely unexpected. And Yang and Li, 2 Chinese scientists living in the US back in the early 70s, theoretically predicted that this property should be found in studying subatomic particles, and at that point the quarks had not been seen yet. And it turned out that that's indeed what happened. Their prediction that there was a left and a right, if you wish, to some of these particles, not a neutral position in space, that once again was a property or a discovery confirmed by the experiment that gave people confidence that the standard model of subatomic physics is right. I mean, there's some fantastic subtleties. I'll show you some examples in a second. So here's a little more detail about the CERN complex. This, of course, is the big ring. And then they have these, they're all defined down here, but they have a proton synchrotron, because the ring uses protons, collides protons. And they need this synchrotron to get the energies up to, say, 100 billion electron volts before it goes in the big ring, where they're now running at, I think, 8 tera electron volts. But you can't just throw a proton in there and say, I'll see you in a microsecond after you've made the circumference. So there's this huge array of stuff going on that feeds the big ring. And then you have the experiments, Alice, Atlas, and I'll also talk about this, Large Hadron Collider B, which B stands for either beauty or bottom. That's an experiment strictly focused on the one quark that's sometimes called beauty, sometimes called bottom quark, and then CMS, which is what I'll talk about most. There's also this interesting little dogleg here that produces neutrinos that are sent over to Italy. So we get a third country involved, and the Italians are 700 kilometers away, and if you imagine Earth, of course, with its curvature, CERN is here. It's a chord of Earth in the direction of this beam of neutrinos, goes over to Gran Sasso, Italy, where they do neutrino research. That's where they had the big controversy about the neutrinos arriving faster than they should, implying that there was something about violation of the speed of light. That problem's been solved. I'll explain it to you in a second. So, once again, the experiments. Alice does ion colliding. And they can produce, now this is really extraordinary, they can produce nucleons at about 3 tera electron volts that are derived from stripping atoms, removing the electrons, and getting a nucleus, and then breaking the nucleus into pieces and getting these pieces up to that volt. And they use lead to do that. So we'll be talking about the compact muon solenoid, and it's a TeV experiment or sensor looking to find the Higgs boson. I'll explain why that's important. Extending and confirming the standard model, and looking for the next generation of model, the supersymmetric model. And they do some heavy ion collisions when they have time. Atlas is also very broad in its capability, and as I said, competes and complements what they do with CMS. So they can, if they see, for example, if CMS sees something at a particular energy, and of course energy and mass are related by c squared, they can get the Atlas guys to go and look at the same place and refine the results. So this is a good time to mention that Frank Lindy, who was a lecturer on the boat, one of his job is to go back through the standard model and refine the properties of the particles that have already been found, but they're in such a hurry moving forward that they don't, it's like doing a survey in astronomy, finding things and then handing over those results to somebody who's going to go study what you found in more detail. So Frank Lindy's group goes and makes precise measurements of mass, properties of the spin, the different quantum numbers that are associated with the particles, and so forth. And then here's the beauty or bottom experiment, and it's just, as I say, totally focused on that particular quark. So maybe a few words about quarks. You probably all have heard the quark theory of nucleons was invented by Murray Gell-Mann and a couple other people back in the late 60s, early 70s, and it says that there are a small family of particles from which you can construct protons and neutrons, and transient particles that are found in these collisions. And I'll show you how this works in a second. But it's extremely beautiful. You have 6 kinds of quarks, and with them you can build the nucleons that make up our world. In fact, there's only 3 particles you need. You need the up quark, to make the universe we observe, you need 3 particles. You need electrons, up quarks, and down quarks. And you can build protons, neutrons, and electrons. That's enough to make atoms. And that's everything we see. There are, other than the up and down quark, there are 4 other kinds, and they are pulled, kicking and screaming, out of the structure of other particles that are observed in these very high energy collisions. And the collisions, when you're at 4 to 8 tera electron volts, you're back to the universe as it was a microsecond after the Big Bang. You're seeing a sea of particles that don't exist for more than maybe 10 to the minus 23 seconds in the accelerator, and they don't exist at all in the world we experience. So, current beam energy, as I said, 8 tera electron volts. The workers at CERN can tell when the beam is running because the power line that comes in from the power grid has big towers with catenaries of wire. When the beam is on, those wires are heated up by carrying the current, and the wire expands, and so the wires are down low. And when the beam is off for some reason, then the wires go back to a normal room temperature, and so they can tell when they're driving to work what's going on. Do they have a question?
Yeah, so back to what you said about these particles, they don't even exist in supernova or neutron stars?
No. No, you have to have extremely exotic conditions. They say at CERN, at the beam colliding point, they are creating the highest temperatures in the universe.
Even when black holes?
Yeah, black holes are relatively cold in the sense that anything that goes in past the horizon and disappears in the hole. So the only time in the history, so this is one way to think about it, the only time in the history of the universe, in the 14 billion years that the universe has been around,